In linear algebra, singular value decomposition shortly SVD, is very famous factorization technique for real matrix. So let's say A matrix, the shape is m by n. We can factorize A in a form U sigma V transpose. So here U, the matrix shape, is there are many definitions, but I will use this definition. U is shape of m by n. Let's say m is bigger than or equal to n, and all the columns of U are orthonormal. So which means if U is consists of n columns, all Ui transpose Uj, so the inner product between two different columns always equal to 0, and Ui transpose Ui, so the length or norm of each column is equal to 1. Okay. V, the shape of V matrix, also n by n. In the case, V matrix also orthonormal matrix, such that Vi transpose Vj always equal to 0, and Vi is equal to 1. And essentially V transpose V is equal to identity matrix with size of n by n. What is this sigma matrix? Sigma matrix is diagonal matrix with all diagonal element is equal to 0, and diagonal matrix, this is some positive number, and each number is called singular value, and each vector called singular vector. Okay, this is singular vector. Right, but left and right matrix have different shapes. So we have left singular vector and right singular vector. Right. So why I explain this? Oh, so another very important concept in linear algebra is when you have A matrix n by n with size what is A transpose A? This is symmetric matrix. Okay, symmetric. But not only symmetric, but also this has positive eigenvalues. All the eigenvalues of this matrix is non-negative. So this is called positive semi-definite matrix. Anyway, what is eigenvalues and eigenvectors of A transpose A? Since A is U sigma V transpose, when you take A transpose A, this is equal to V sigma U transpose U sigma V transpose. Since U is orthonormal columns, consists of orthonormal columns. This make identity matrix with size n by n. So essentially this is equal to V sigma square V transpose. So when you multiply Vi to A transpose A, this is equal to I singular value square, I singular value of A matrix square times Vi from this. So Vi is an eigenvector, Si square is the corresponding eigenvalue. So all S1 square, S2 square, Sn square, they are eigenvalues of A transpose A. V1, V2 up to Vn, they are corresponding eigenvectors of A transpose A. Similarly, you can derive eigenvalues and eigenvectors for A transpose. This again, when you multiply Ui, this is Si square Ui. So A transpose also has S1 square up to Sn square eigenvalues and U1 through Un eigenvectors. So right singular vectors comes from the eigenvectors of A transpose A. Left singular vectors comes from eigenvectors of A transpose. Okay, and also we have this. When you want to maximize this equation, the solution is when x equal to u1. Sorry. When x is u1, x A transpose x is equal to S1 square. That comes from the definition of eigenvalue, eigenvector, and singular value and singular vector. Why I explain this? Because this concept has strong connection to principal component analysis. Okay? As I explained in the previous video, essentially the principal component is the solution of this. Sum of I through n pi transpose xi square. And this is sum I1 to n pi transpose xi transpose pi. And very interestingly, this is equal to this when you define a matrix X using this. This term is equivalent with pi transpose X transpose pi. So how can maximize this? Well, the solution is the eigenvector corresponding to the largest eigenvalue of x transpose. This is equivalent with when you take singular value decomposition of x. So when you have U sigma V transpose for matrix X, then U1 corresponding to the largest singular value, this should be pi. This should be the first principal component. That will maximize this, and that will minimize the total distance between the data point and projection point. Okay? And in this way, you can define many principal components, as many as you want. After you extract the first principal component, so for instance, in this case, when you have data point here, and you have this axis, and you have this first principal component. After extract the first principal component, you have this residual term. So if it is allowed, maybe it is good to have another direction to describe this residual information, because the residual part can help you predict something for your machine learning. Okay, so you have to find another principal component that will describe this residual value. This is called second principal component. In this way, likewise, you can define third principal component, fourth principal component, and so on. But don't worry, once you find singular value decomposition of your data matrix X, then what is the second principal component? This is the second singular vector. What is the third principal component? This is the third singular value. So basically, principal component analysis is equivalent to singular value decomposition. When you have the decomposition of your original matrix, your data matrix X, in singular value decomposition form, all the singular vectors will give you very nice principal component. Okay.